This is NMR 300, again trying to assimilate the instructor. Assimilation process is underway. Instructor will be assimilated. Wait, what is happening? Man, I had to saw my way out that time. That pesky NMR 300. Always getting into trouble there. Well, anyway, let's get back to interpretation of NMR spectra. And we're going to talk about another really useful aspect. So far, we looked at chemical shift, which is where the signals would show up, here, here, or here. We looked at the number of signals. Do you have 1 or 2 or 3 or 4 or 10 types of hydrogens or carbons in your spectrum? Now we looked at the area of the signals. Are they tall signals or short signals? Are they narrow or wide? Now here's where we get a lot of information from. And this is going to be what's called spin-spin splitting, splitting of signals. Sometimes it's also called coupling of signals. And this happens when different types of hydrogens are right next to each other. And so let's take a look here. So here's ethane. We saw that before. Turns out ethane, every single hydrogen is in the same exact environment, and you end up with what we call a singlet. So just a little single peak right there. And if you label the types of hydrogens, every single one of them would be HA, all the way around there. Now if we throw in some bromines, we'll just mix it up a little bit, throw in some other atoms, there's really no difference between what this hydrogen experiences and this one. Those guys are both in the same environment. You're going to get a signal. Now we're changing things. Now if chlorines on one side, bromines on the other, these guys experience different environments. So now we have HA and HB. And so we know we're going to have two signals, one for HA, one for HB. So we can say that. We can say, okay, HA might be here, HB might be here. Actually, more likely that HB is here because he's near the more electronegative chlorines. We know we have two signals. Now, what do those signals look like? They're not going to be single peaks, it turns out. Here's why. So here's what HA is going to see. So I'm going to draw what's called a splitting tree. HA gives you a signal. HB will give you a signal. HA sees the magnetic field from the instrument. It also sees another magnetic field. It sees the magnetic field from HB. HB could be spin up or spin down. So here's what HA sees. HA sees the applied field plus two possibilities for his neighbor. The neighbor could be up or down. He's seeing two different possible spin states. And what happens? He sees two slightly different magnetic fields, and his signal gets split. And that signal is then called a doublet. And what that tells us is that HA has a neighbor. That's a useful piece of information there. And it turns out the same thing happens with HB. HB sees the applied field of the instrument, and he sees the field from the hydrogens next door. And so what happens is HA is split by his neighbor. HB is split by his neighbor. Remember, neighbors will communicate with each other, so it's always a two-way street. So you have HA who lives on this carbon, HB who lives on this carbon, and they'll talk to each other across their white picket fence or whatever. And so that splitting will occur, and you can actually tell how many neighbors are next door by the splitting. So let's take a look here. So we have HA again. HB meets someone and they move in together. And so now HA lives on this carbon. HB, this couple here, they live on this carbon. So they are neighbors. So HA has two neighbors. HB, they have one neighbor. So here's what's going to happen to HA now. HA has a signal, but HA will also see all the spin states from HB. So here's the possibility for HB. You got two of them, remember? There's two HBs. They could both be spin up. That's one possibility. They could both be spin down. Or one could be up, one could be down. Or one could be up and one could be down the other way. Statistically, there's two ways to do that. And so you end up with three possibilities. If they're both spin up, it's going to see this magnetic field. If one's up and one's down, they kind of cancel each other out. If they're both spin down, you'll see a slightly smaller magnetic field. And so HA is now split into three peaks. We call that a triplet. And we'll draw that on our little splitting tree here. HB only sees one neighbor. HB has one neighbor living on that other carbon. So we're still going to see a doublet. So here's what that splitting tells us. It tells us how many neighbors there are. And don't forget, there are two HBs and only one HA. So that affects the size. So if we're going to simulate our spectrum, the HA signal will be smaller than the HB signal, and it'll be a 1:2 ratio. But let's say here's HB. Let's see, they have a kid. Now we have three neighbors next door to HA. So we have a family of three HBs. So these guys are all in the same environment, and this guy's in another environment here. So we have three neighbors next to one neighbor. Now, here's what happens. You've got all those HBs there. Here's your possibility. They could all be spin up. They could all be spin down. You could have two up and one down. And there's a few ways to do that. Or you could have two down and one up. And again, 1, 2, 3, 4 possibilities there. And so what happens to HA, now that he has three neighbors, he gets split into 4 peaks. And those peaks actually will have within them a 1:3 to 3:1 ratio, because there's one way to do this, 3 ways to do this, 3 ways to do this, 1 way to do this. There's only one way to have all three of them pointing down. There's only one way to have all three of them pointing up. HB, they still only have one guy living next door, so you're still going to see a doublet there. And so here's what our spectrum will look like. We'll have 4 peaks. We call that a quartet. And then we'll have a fairly large doublet in a 1:3 ratio. That's called spin-spin splitting. And so what's happening is HA is being split by 3 HBs. HB is being split by 1 HA. And one other interesting thing, the spacing right here, this is called a coupling constant. That spacing is going to be exactly the same if these guys are neighbors. So that's a coupling constant, sometimes given the symbol J. And many times you can look up standard coupling constants. So when you have those neighbors, you can tell who's next door by the number of peaks within your signal. So this is the world of spin-spin splitting. It's going to give you more information than you ever wanted to know. And it gives us something called the N+1 rule. So splitting is always determined by your neighbors. And it turns out, you count up your neighbors, plus 1, that's going to be what your signal gets split into. If you have no neighbors, you will be a singlet. You'll have 1 peak. If you have 1 neighbor, you'll have 2 peaks. 2 neighbors, you'll have 3 peaks. 3 neighbors, you'll have 4 peaks. and so on. It can keep on going, actually. You can have like 6 neighbors if you want on the carbon on the other side. And so we call this guy a singlet, a doublet, a triplet, and a quartet. So that's called the n+1 rule. And one of the interesting things about the shapes of these signals is you can predict the size of the peaks within the signals based off of this interesting triangle here. This is called, think back to your math classes, pause for a second. Did you come up with Pascal's triangle? Because that's what this is. Blaise Pascal came up with this triangle, and there's a picture of him looking at this triangle going, hey, that's a pretty cool triangle right there. Maybe someone will name it after me. So this is Pascal's triangle, and what's interesting about it is it gives you the shape of those split signals. So here's a typical singlet. It's just a single peak. A doublet will typically have 2 peaks about the same size. A triplet, you'll usually see 1 to 2 to 1 ratio within the signal. A quartet, you'll tend to see a 1 to 3 to 3 to 1 ratio. Let's see, this guy is a pentet. And here's 6 peaks, that would be called a sextet. And so Pascal's triangle actually gives you that ratio within the signal, the number of peaks in a signal. And the way you generate these numbers is this 3 is 1 plus 2, this 6 is 3 plus 3. You just add up the 2 numbers right above it to get the number below it. One thing that's interesting though is that in something like a sextet, you actually have a 10 to 1 ratio when you're looking at the outer peak to the inner peak. Sometimes if your baseline is noisy, you might not see those peaks. Allow yourself a little bit of flexibility there. So don't strictly count up the peaks. These are very ideal spectra that I'm picking here. I'll show you some messy spectra later on. Because sometimes you do get peaks that look like this. What's that? A triplet, a quartet? I don't know what's going on there. You know what we do with that? As spectroscopists, we'll say multiplet. Lots of splitting. That's what we can say for now. So that splitting will tell us a lot about our compound and allows us to actually put things together. So let's take this for a ride here. So we've got this compound, and this one has a formula of C4H8O. So we're going to go into it with that piece of information. And one of the first things you really want to look at, you can look at the number of signals. We know that we have 1, 2, 3 signals, 3 types of hydrogen on our spectrum. Then what we do is we look at the integration. And the integration is where we look at the signal height. Now take a look, we do have those integration lines running through here. And so I start to construct my hydrogen ruler. So I ran a line right through here. I'm going to put one up here. And notice the spacing here is different than the spacing here, so I'm going to throw in an extra line. So this is my ruler. And what you'll notice is you have remember, we're not going by the height of the signal, but by where that integration line goes. The integration line actually starts up here. And you can see it in the expansion down below. This signal is this guy, that's that one, and that's that one. And these 2 signals are up here. So this is a 2 to 3 to 3 ratio, which is the same as 4 to 6 to 6. However, we know we have C4 H8, 0. 2 plus 3 plus 3 gives us our 8. So we're going to stick with that as our integration value there. So now we can start putting this guy together. Here's how we'll do it with the splitting. C4H8O. And what this is telling us, we have 2 hydrogens here on our quartet. We have 3 hydrogens in a singlet, 3 hydrogens in a triplet. Let's look at our pieces here. 3 hydrogens by themselves, well, that can just be a CH3 group. So that's a piece of our puzzle. That only leaves 3 carbons to deal with. And let's take a look at this. We have a quartet. If you have a quartet, you've got to have 3 neighbors. If you have a triplet, you have to have 2 neighbors. Remember, it's number of neighbors plus 1. The neighbors have to be neighbors. They got to be next to each other. So I'm going to put 2 neighbors next to 3 neighbors. This is the characteristic splitting pattern of an ethyl group, C2H5. So that's another piece of our puzzle. It only leaves us with carbon and oxygen. So the last piece of our puzzle has to be a CO double bond. That's our compound right there. We just put these 3 pieces together, and there you go. This is called methyl ethyl ketone. You can actually buy this at Home Depot or Ace Hardware. It's a common paint stripper, good all-purpose solvent there. And now you know what the NMR spectrum looks like. And so that's where the splitting helps. So notice there was no splitting here because HA does not have a neighboring hydrogen. There's no hydrogens on this carbon. So those 3 hydrogens are just showing up as a singlet. This guy right here, he's showing up as a 2 hydrogen quartet. This was a 3 hydrogen singlet, 2 hydrogen quartet. HC is a 3 hydrogen triplet, which is this guy right here. So that's a characteristic splitting pattern. What I want you guys to do in your notes is start a page that says characteristic splitting patterns. You're going to see this a lot. If you have a triplet and a quartet in a 2:3 ratio, that's an ethyl group. That's a dead giveaway of an ethyl group right there. You can say, aha, ethyl. Let's try this again. And this time with this compound, this will be C4H8O2. This is going to be a similar compound. I'm not making this one too different. Again, we have 3 signals. Let me get my head out of the way here. There we go. And again, we've got a quartet right here. We have a singlet. We have a triplet. And we actually have the same integration going on. Here's the top of an integration line, the bottom of the line, top of the line, bottom of the line, top of the line, bottom of the line right there. That's an integration line. So let's put in our rulers. It's going to be similar to last time. You're going to end up with a 2:3:3 ratio. Remember, we're looking at the peak area, not the peak height. That's a really important distinction there. So we have a 2:3:3 ratio. And remember, we have C4H8O2. So we're actually going to have a lot of the same pieces. We actually have a CH3 group. We also have that ethyl group. That ethyl group is still there because we have that triplet and quartet. That's going to leave us with carbon and 2 oxygens. When you go to put this guy together and still follow the octet rule, your last piece of the puzzle is going to be an ester. That allows us to narrow this guy down to 2 possibilities. It's either this guy or this guy right here. So either one has an ethyl group. And the way we split the difference is we have to look at the chemical shift. We have to go back to our correlation table. Turns out something showing up around 4, that's most likely going to be a hydrogen attached to a carbon attached to an oxygen. And let's look at the 2 possibilities. This guy right here is a quartet. This fellow is a singlet because he doesn't have any next door neighbors. There's no hydrogens on that oxygen. That means this has to be our compound. It has to be that one. So you can put these molecules together two different ways, but only one's going to match our spectrum. And it's got to be this guy. This is ethyl acetate, commonly found in paint strippers and nail polish remover. And again, what's happening here, our HA is a singlet because there's no hydrogens over here, so he's isolated from everyone else, no neighbors, he's by himself. And so that's going to be our singlet, a 3-hydrogen singlet. It's usually how we'll designate it. This guy right here is going to be a 2-hydrogen quartet. And then we're going to have a 3-hydrogen triplet. So we can put our compound together that way. And when you look on your correlation table, you'll see a hydrogen in this position right here will show up around 4. A hydrogen in this position will be around 2 to 2.5 according to our correlation table. So we go back to our correlation table to break a tie. If we switch this around so that we had carbon, carbon, then a carbonyl, then an oxygen and a carbon, we would see that our singlet was showing up at 4. That's the difference there. So this would be at 2 to 2.5. A hydrogen here would be around 4. So we use that correlation table to split the difference. Again, we can put these together. This is a logic puzzle, what we're doing right here. If you like logic puzzles, NMR is for you. If you don't like logic puzzles, I apologize. Let's look at something a little different here. This guy will be I'm trying to remember the structure here. C7 H7OBr. And again, we'll take a look at number of signals. We've got 3 types of hydrogen. We know that. We also have our integration lines. Notice here's the top of the step. You can't see it too well over here, but you can see it down here. So I'll add my little ruler in there. So our 2 doublets over here, so these are doublets, are actually integrating that high. And then we have the singlet over here. It's a little bit higher, but notice the spacing is different. So I'm going to throw in another part of our ruler. And what we end up with is a 2 to 2 to 3 ratio. And what that tells us is that we have 2 hydrogens in this environment, 2 here, and 3 here. Now here's something interesting. 7, this has to be an aromatic ring. And we have to have 4 hydrogens on that ring. So that means one of our puzzle pieces looks like this. Ooh, that's an ugly looking ring there. Okay, let's clean that up a bit. So that's one of our puzzle pieces. So we had C8, now let's make that C7, H7OBr. We just figured out what to do with 6 of our carbons and 4 of our hydrogens. Gee, what can we do with these 3 hydrogens? How about a nice handy CH3 group? And that only leaves an oxygen and a bromine. So we've got a CH3, we have an oxygen and a bromine. It's going to be kind of rare that you stick an oxygen on a bromine. 2 electronegatives connected together, not so stable. I'm also going to take a look at the shift here. Round 4, this is usually a hydrogen connected to a carbon connected to an oxygen, according to our correlation table. So I'm going to stick these 2 guys together and make a bigger puzzle piece. I'm going to say this is a methoxy group. Now I have 3 pieces on my puzzle. And there's only a few ways to arrange this. I can do this. I can do this. Or I can do this. Three possibilities here, just by using some deductive reasoning and logic. So this is kind of a quantitative reasoning process. You may have done standardized tests like this. And you may have seen a standardized test like there's 5 desks in a room. Bob likes to sit next to Jane. Jane likes to sit on an end desk. Jim likes to sit next to Mary. Bob can't sit next to Mary because of the restraining order. And you gradually use all these parameters to put people in their seats. You're doing the same thing here using this splitting. And so we have these 3 possibilities, but we notice we've only got 3 signals here, a singlet and 2 doublets. The only possibility is the one that has a lot of symmetry. That's this guy right here. This is our compound. And notice we have a plane of symmetry running through here. And so we actually have 3 types. I'm going to cross that out. That's HC down there. So we have HA showing up here. HB, that shows up right here. I'll show you why that does later on. And HC showing up here. And so what happens, HB has 1 next door neighbor. So he's going to be a doublet. HC has 1 next door neighbor. He's going to be a doublet. The fact that you have 2 HBs just means that those doublets show up at the same spot. This HB experiences exactly what this guy does. So you end up with a doublet here, singlet over here. So you just count up the nearest next door neighbors. And that way you can put your compounds together. And so what we've been looking at are characteristic splitting patterns. And this is a characteristic splitting pattern when you have 1,4 substitution on an aromatic compound. You'll actually see a pair of doublets in the aromatic region. That's like a dead giveaway. They have an aromatic ring with 2 different groups on it. I'm going to show you something else. We've already seen this. This is an ethyl group if you have a quartet and a triplet in a 2:3 ratio. If you want to see a lot of splitting, here's an isopropyl group, because you have this guy right here. He's HA. He has 1, 2, 3 neighbors on this side and 3 more neighbors on this side. These guys are all equivalent. This is HB, 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 HB. So there's lots of splitting here. So HA gives you 1, 2, 3, 4, 5, 6, 7 peaks, if you can make them all out there. So that would be a septet. And HB, this guy only has 1 neighbor. HB can only see this guy living next door, so he's a doublet. But you have 6 HBs. And so that gives you a really tall signal, and you only have 1 HA. So this is a 1H septet, or multiplet. Usually you can't see all the peaks. So I'll write multiplet there as well. And up here, you have a 1 hydrogen doublet. So if you see that doublet, the giant doublet next door to a small multiplet, that's typical for an isopropyl group. It's dead giveaway for that. It's a characteristic splitting pattern. So you can start to recognize these bits and pieces that show up in lots of different molecules. And so think of it this way. HA is surrounded by lots of neighbors here. So maybe he likes to have a nice quiet lifestyle. But then these guys get together and have a big party, and they're going to give him a splitting headache. So that's what happens when you have lots of neighbors. And I'm going to show you some more characteristic splitting patterns next. This time we'll be looking at some aromatic compounds.